Hi everybody, welcome to another video in differential equations, section 7.6, transform of discontinuous function. First we define a unit step function as a script u of t is equal to 0 when t less than 0 and is equal to 1 when t greater than 0. So if I need to draw that, so the function will be equal to 0 when t is less than 0 and equal to 1 where t is bigger than 0. And this is also a switch, just like the switch when 0 is off, and when t equal to 0 we turn the switch on and the value is 1 and so on. Right, so that is a switch. Anything left of 0 is 0, anything greater than 0 is, for t is 1. Right. Now we define a rectangular windows function. That is the windows from A to B is equal to 1, everything else is equal to 0. So this is equal to, the whole function is equal to the window of t minus A minus the window of t minus B. So how does that work? Right. So the windows, by the way, when we write like this, A and B being positive. So A and B. So we have the function equal to 1 when t is between A and B and 0 everywhere else. Yeah, so 0 on the left of A and on the right of B. And later on we'll see that it doesn't matter what is it on the left of 0 or not, because on the Laplace transform it is defined from 0 to infinity, right? The definition of Laplace transform. And also remember, when we do the Laplace transform for the derivative, we need the initial condition. So it is important that we only go from 0 and up. So anything less than 0 is not important, because when we do the Laplace transform, that doesn't factor in the Laplace transform. So how does this work? Now if you think about this, first of all, we for this function we start with u of t minus A, right? So first we start with u of t minus A. Meaning that it will equal to 0 if t minus A less than 0, and it is equal to 1 if t minus A greater than 0, right? Exactly from this definition we write like that. Now when t minus A less than 0, meaning that t less than A, and here we have t greater than A, or we write this is equivalent to equal to 0 if t less than A and equal to 1 if t is greater than A. So this function is equal to 0 if it's less than A and equal to 1 if it is greater than A. Right? So we have that first part here, use of t minus A, is that but this function dies off after B. So after B, it's going to be 0. So how do we do that? So meaning that after B we have to delete that part, and this will go off and equal to 0. So how do we do that? So just like if you have a piece of paper and you draw a circle, and then I ask you, how do we move the circle here to there? Because what we do is first we will erase that circle and then we just draw that over there. Right, so that's kind of exactly what we do here. So if we want to erase that, we have to do exactly the same thing, but it will be 0 on the left of B. And on the right of B, it have to be opposite to this. Right? So, if it's on the left of B, it's nothing. But on the right of B, we will add the -1 to the function. And the 1 here with the -1 cancel out. So that is like we erase that. And then we start a new function. So with that, the windows from A to B is the values of u of t to A and then minus u of t to B. So if I have to write this again, the first part here is equivalent to 0 if t less than A and equal to 1 if t greater than A. And then we have a subtract. Now we have this function. It will be equal to 0 if t less than B. And it will be equal to 1 if t greater than B. So what it does is, original it go from 0 if less than A. And then from A to B, it will go to 1. And then when it's greater than B, we have 1 minus 1. So that's why we go back to 0. Right? That's how we write the Windows function. Again, original we start from 0, and then we switch on. But then we have to switch off by doing the negative. And delete this part. That's why we have these two functions. Right. Now, as mentioned before, Laplace Transform is interesting because we define that only from 0 to infinity. So actually, we don't really care what happened if it's less on the left side of 0. But besides, most of the application dealing with time, and time cannot be negative. So on the Laplace Transform definition, it goes from 0 to infinity. So because of that, we only go from 0 to infinity. Right. So the windows A, B, meaning that it will be equal to 1 if it is between A and B, and will be 0 everywhere else. So let's look at this. Express this following function using the step function. Right. So we say the function is 0 if it is between 0 and 4, and is equal to t plus 5 if it is greater than 4. Right. So just look at the function. It will be equal to 0 from 0 to 4, right? So meaning that the function is equal to 0 times the windows pi 0 to 4. So from 0 to 4, take the 0. And when it's greater than 4, it is t plus 5. So we just have t plus 5. And then for greater than 4, we just have the windows of t minus 4. So, and then 0 times anything is 0. So that's why this one gone. Right? So when we have a piecewise function, write that as a windows function. And then use these properties. The window from A to B of t is equal to u of t minus A minus u of t minus B. Right. Now, look at the next example. Express the following function using unit step function. So first, look at t squared from 0 to 2 easily t square the window from 0 to 2. Right? And next we have 6 when t greater than 2. If it is greater than only, we're going to use the u of t minus whatever that number is, because t minus 2 t greater than 2 is equivalent to t minus 2 greater than 0. So we just have that function here, right? So if it is between two numbers, use the pi, the windows function. If it's just greater than, move that to the other side, and we use the unit step function, right? Next, the windows from A to B is written as the window of t minus the left values minus u to t minus the right values. So we have u of t here, because that is equal to u of t minus 0, or just u of t. So t square, the window would be on u of t minus the left values minus u t minus the right values, u t minus 0 minus u of t minus 2, right? Then t square. And then so we have just multiplied now t square, u of t minus t square, u of t minus 2 plus 6 u of t minus 2, and then common factor of t minus 2, factor it out, and that's what we have. By the way, why do we write here without the u of t? Because u of t is equal to 1 when t greater than 0. As mentioned before, this function we only worry about when t greater than 0, because after we write this the function like this, we use the Laplace transform right after that. So in that case, we really don't worry what happened on the left of 0, because on the left of 0 the function is equal to 0. So in that case we can say u of t is equal to 1. Later on when we do the Laplace transform, actually it will be consistent to the way we do it. Right, so when we have the piecewise function like this, so set it piece using the unit step function or window function, and after that we split the windows using this, and then we combine them. Right, before we do that, just want to look at this function. Let's see. So originally it goes from 0, and when from 0 to 2 the function is t square. But after that, from t square on, the function is equal to 6. So first we have to get rid of the t square. So from here on the 2 on, we have to subtract the t square first to bring this back to 0. So that's the first thing we do. And also when t greater than 2, the function is equal to 6. And we see from 2 on we have negative 2 square and then plus 6. So that's why we have from for u of t minus 2, or from t greater than 2, we have 6 minus t square. So first we get rid of the t square, and then we add the new values. So get rid of the t square and then add the new values. So that's what we see here. Right, but we don't even need to graph it. The proper way to do this is first we'll look at the windows here from 0 to 2. It is equal to 3, meaning we will have 3 times the window from 0 to 2 of t, right? And then plus, it's going to be t square plus t square from 2 to 5, and we have t square times the windows from 2 to 5. And after that, we just have t plus 7, t greater than 5. When it is greater than, we just going to use, when it's greater than, we're just going to use u of t minus 5. Right, so if we have between two values, use the windows. If it is greater than, use the u. Right, so that's the first step for every piecewise function. That's the first thing we do. Right, next, now we use the windows function. The windows is the unit step function of t minus the left values minus unit step function of t minus the right values. So we have u of t minus the left minus u t minus the right. Right. Next, we have t squared. First, this will be the windows. The unit t step function of t minus the left values minus unit t minus the right values. Right. The last one, I will just keep it because that is just a unit step function already. We don't need to do anything there. Right. Next, as mentioned before, u of t or u of t minus 0 is equal to 1 because we're interested in the function when t greater than 0 only. So this will be u of t is equal to 1. So we just have 3. So we have 3 times 1 minus 3 u of t minus 2. Right. Next, plus t squared of u t squared u of t minus 2 minus t squared of u of t minus 5. Then just plus that. Right. Now combine. Just factor this out. So we will have 3 plus minus 3 plus t squared u of t minus 2 plus factor this out minus t squared then plus t plus 7 u of t minus 5. Now if we think about that, originally is 3 and then we have to turn up the 3 and we start with the t squared. After that we turn up the t squared and we add the new t plus 7. So that's the way it works with the piecewise function, and we rewrite that using the unit step function. Because the way we do that, use the window first and then write that as everything is unit step function. Of course that function only for t greater than 0. Because we do that so we can let u of t equal to 1. Right? Yeah, so almost we can do this without doing any of this. We start with 3 and then at 2 we turn off the 3, turn on the t squared, and at 5 turn off the t squared and turn on the t plus 7. So almost that's the way it works like that. So it's not that bad. Now what bad is when we combine all of this together into one big differential equation. Then we just have to do step by step, do the little things. A lot of little things. Right. So first, what we focus now is write this as the unit step function. So first, we have t cubed from 0 to 1, right? So that's easy. We have t cubed times the window from 0 to 1. Next, the next piece, it is 0 from 1 to 3, right? So 0 times the windows from 1 to 3. And then 2t when t greater than 3. So in that case, we do not need the windows function. We just want to say 2t u of t minus 3. Right. So if it is just greater than, don't use the window, just use the u. And let that greater than 0, so t minus 3 greater than 0 or t minus 3. Right. Because 0 times anything is 0. And now we'll rewrite this windows using the unit step function. So t cubed, the windows from 0 to 1 is t minus 0 minus u of t minus 1. That is 0. And then we have 2t u of t minus 3. And u of t minus 0 or u of t is equal to 1. So multiply this out. We have t cubed times 1 and t cubed times that. Do that. And then 2t u of t minus 3. Right, so looking at this, we turn on the t cube at 0, and then when t equal to 1, we turn off the t cube. And then when t equal to 3, turn on the 2t. So that's what it is. From we turn on the t cube at t greater than 0. When t greater than 0, we turn on the t cube. And then when t equal to 1, turn it off. So minus t cube when it's greater than 1. And then on the way to 3, we turn on the 2t. So that's how it works. Yeah. We will see more piecewise function, and then we'll just want to do that. So for each piece, if it is between two numbers, use the windows function. If it is greater than, use the unit step function. And then write the windows as the difference of two unit step function. And then just simplify, combine like terms. So simple enough. Right. Now, what's important thing is, what is the Laplace transform of a unit step function? Well, Laplace transform of the unit step function of u t minus a of s is equal to e to negative as of 1 over s, and here's the proof. So Laplace transform using definition from 0 to infinity. So the thing is, by the definition of Laplace transform only go from 0 to infinity, so that's why we don't really need the case where we have t less than 0. So we can just let this equal to 1 when t greater than 0. When it's less than 0, it doesn't matter. Right, so now we have this function, right? Laplace transform, definition of Laplace transform. Now this function is equal to 1 from 0 to infinity. Okay, let's write this function out. This function is equal to 1, I mean equal to 0, if t minus a less than 0, and equal to 1 if t minus a greater than 0. which is equivalent to 0 if t is less than a and equal to 1 if t is greater than a. So that's why we have a here as the limit, because when t greater than a, the function is equal to 1. When t less than a, it is equal to 0. The integral therefore equal to 0. Right, and then we just integrate and improper integral, integrate and then put in the limit, and then essentially this equal to e to negative st of 1 over s. E to the negative sa, or e to the negative as 1 over s. Now, of course, if we just have, what happened if we just have the transform of u of t? Of course, definition, integral from 0 to infinity e to negative st u of t dt. Now u of t is equal to 1 when t greater than 0, so this is equal to 1. So it doesn't do anything if the function is equal to 1, right? When t greater than 0, or u of t, that is just equal to 1. Yeah, so that's why when we have here, when we have u of t minus 0 or u of t, we're just going to let that equal to 1 and assume that t is positive. Right. So that's good. We have the Laplace transform of the unit step function, which is here. If you cannot type the script u, use the lowercase u. Right, now, of course, it is more interesting if we just do the Laplace transform of the function times the unit step function, right? So like we do Laplace transform of something like this, for example. And how do we do it? Right, now, the theorem, translation in t. If the function is Laplace transform is equal to that exists for s greater than alpha. If a is a positive constant, then Laplace transform of the function of t minus a times unit step function of t minus a to s equal to e to negative as f of x. Right. That's nice and all, but I highly recommend that we don't use that formula and we use the alternative form. Use this one instead. It is a lot easier to apply. Right. So when we see that, the first thing is we will turn, when we see the unit step function in the transformation, first thing we do is we're going to write e to negative as. So that will turn into two components. That's the first thing. And then second, g of t becomes g of t plus 8. You will see that the g of t plus 8 is a lot easier than find out the f of t minus 8. It will be much better using this instead. We'll see. And conversely, when we do the Laplace transform of this, so first thing, every time we see the e to negative as, this turn into two things. First, it will have the unit step function of t minus 8, and it will just do the transform of f of s, and we have to do two things. The t replaced to t minus 8, and then multiply by the unit step function of t minus 8. So that's what we end up to this. Right. So we have a few examples, don't worry. So first let's look at the first example here. Find the Laplace transform of 3 from 0 to 1 and t when t greater than 1. So first we have to rewrite this as the unit step function, right? It is equal to 3 from 0 to 1, so 3 times the windows from 0 to 1, easy, right? And then t greater than 1, so t unit step function of t minus 1, right? Between 0 and 1, use the windows. Greater than 1, use the unit step function. And then the windows we write using the unit step function, and u of t equal to 1. and then just multiply it out, and then combine like terms at the end. That's what we have. So this is a function. Now we will find the Laplace transform for this function. Right, Laplace transform of this. Yeah, I'm missing a parentheses here. Sorry. Right. First, we split this in two because Laplace transform is linearity. It's linear, so we can split the Laplace transform of 3 and Laplace transform of this. So now remember, we will use the alternative form, and so we have to write g of t instead of using that. So when we have this, we have the unit step function of t minus 1 and then t minus 3. So what we do is we're going to let this be g of t. So g of t is equal to t minus 3, right? And a is equal to 1 in this case. So g of t is t minus 3. So g of t plus 1. So simply I just put t plus 1 into t. Right? So instead of t, I will have t plus 1 minus 3, so t minus 2. So bottom line is Laplace transform of 3 is 3 of 1 over s. So that's easy, right? Laplace transform of 1 is 1 over s. So Laplace transform of 3 is 3 over s. Sorry, this should be a curly bracket. And then when we write this, we have u of t minus 1 will turn into e of negative s. Right. When we see the unit step function, that will be e to negative s. That's the transform. And then whatever function we have for g of t plus 1, we're going to find the Laplace transform of that. So we do the Laplace transform of t, Laplace transform of 1, Laplace transform of t is 1 over s squared, Laplace transform of 1 is 1 over s, and we have 2 over s. So that's what we do. So first thing, when we see Laplace transform of something like this that has the unit step function, first thing we do is that this we turn into e to the negative pi s. And then we do Laplace transform of g of t plus a. So what is t plus a? You say, right, now what's left in the function is g of t. So let g of t be cosine of t. Right. Now what is a? Well, in this case, a is whatever that number is. Just in the last form, a is 1. So in this case, a is pi. Yeah. So when we have the unit step function of t minus pi, a is equal to that, and then we have e to negative as. Right. Now if g of t is this, we need g of t plus a. So what is g of t plus a? Which is g of t plus pi. Right? Because pi is a. Right. So to recap, when we see the unit step function, replace that with e to negative as. So we know a. What's left of the function is g of t. when you have g of t, try to find out what is g of t plus a, just this. Now we can put in the function cosine of t plus pi right. Now we have a cosine of a sum. Now this will come in handy. Cosine of a sum, it's going to be cosine A cosine B minus sine A sine B. So we continue with cosine of t, cosine of pi minus sine of t, sine of pi. Now sine of pi is equal to 0, cosine of pi is negative 1. So all of that equal to negative cosine t. So cosine of t is equal to g of t plus a. And we will substitute into that. Now to recap, let's rewrite the problem again. Laplace transform of cosine of t, unit step function of t minus pi equal to, once again, first thing, this is e to negative as. Laplace transform of g of t plus a, which is negative cosine t. Right, so that's a lot easier. So once again, this will be g of t, and this will be g of t plus a. Right, so Laplace transform of the unit step function times something will be e to the negative as, and then Laplace transform of g of t plus a. So we need to find g of t plus a first. So this will be a lot better than try to write this as f of t minus 8. If we try to write this as the function here, will be less intuitive. So I prefer to use this alternative form. Right, because we take the negative outside, and then Laplace transform of cosine of t. So we have negative e to negative pi s. Laplace transform of cosine of t. Cosine is even. Laplace transform going to be an odd, so it will be s square plus 1 square. So that is the Laplace transform of cosine. Right. Right. So next, Laplace transform of this function. So we have t squared times the unit step function u of t minus 1. T squared times u of t minus 1. Right, so first we have u of t minus 1 here, replaced as e to negative 1 s. So here a is equal to 1. Yeah, those numbers should be positive. Right, so, and then what's left is just the transform of g of t plus 8. So we need to know what is g of t plus 8, where this is g of t. So let g of t be t squared. Now, we will find g of t plus a, where a is equal to 1, so g of t plus 1. G of t plus 1, we put t plus 1 into t here. Right, so that's easy, just multiply now. We don't need a trig identity here. Let's just write out t plus 1 times t plus 1. That gives us t squared plus 2t plus 1. So that is, and we're going to substitute that into g of t plus a. Right, so to recap, Laplace transform of t squared u of t minus 1 is equal to u of t minus 1 becomes e to negative s, and then Laplace transform of g of t plus a, that. So that's easy, right? So we just split the Laplace transform. Right. Laplace transform of t squared. So we'll have Laplace transform of the power of t. So t is 2, so I have 2 factorial over s to the n plus 1, so s cubed plus 2 times the Laplace transform of t, 1 factorial s squared, Laplace transform of 1 over s. So multiply that all out. Just simplify this. 2 over s cubed, 2 over s squared, and 1 over s. Right. So once again, originally we have g of t. Just need to find g of t plus 1. Or g of t plus a. Right. So that's what we do. Next, we find the Laplace transform of this one. Once again, there's the unit step function. So that would turn into the exponential form, exponential function. So this will be equal to u of t minus pi. We have e of negative pi s, because in this case a is equal to pi. Right. What's left, we need to have the Laplace transform of g of t plus a. So we need to find g of t plus a, where g of t is equal to sine of 2t right. So g of t plus a, or g of t plus pi equal to, instead of t here, we're going to have t plus pi. So sine of 2 t plus pi. Multiply the 2 inside, we have sine of 2t plus 2 pi. Now, here we have the sine of a sum. So let me write out the formula for the sine of the sum. Sine of a plus b equal to sine A cosine B plus cosine A sine B. If it is the minus, it should be minus, and similarly, if this is a minus, it will be a plus. Right. By the way, this is just sine of 2t, because the period of sine is 2 pi, but that's of course. Now just apply that formula, sine of 2t cosine of 2 pi or cosine of 0 plus cosine of 2t sine of 2 pi. Cosine of 2 pi or cosine of 0 is equal to 1. Sine of 2 pi is equal to 0. So this would be 0, and that just would be sine of 2t. Right. Now go back to our problem. Laplace transform of sine of 2t u of t minus pi. First replace this with e to negative pi s, and then Laplace transform of g of t plus a, g of t plus pi, or sine of 2t. Right, so we have e to negative pi s. Laplace transform of sine of 2t. Sine is an odd function. Laplace transform be even, so we have 2 s squared plus 2 squared. So that's what we have. Right. So that is where we do the Laplace transform. So what happened if we have to do the inverse Laplace transform? So when we do the inverse Laplace transform, we do two things. First, when we have to have the e to negative as. So first, that turn into a unit step function u of t minus a, and then transform the function. But after we do the transform the function, replace t with t minus a. So we have to do two things. Right. So this is where we do the Laplace transform in Laplace transform. Unit step function turn into e. Right, now we do the inverse Laplace transform. Find the inverse transform for that. Right, so first we write like this. So when we see the e to negative something s, there will be two things. This is 2. So first we have u of t minus 2, and then do the transform of what left, but at the end have to have t replaced by t minus 1. So we do 2 steps here. This is t replaced by t minus a, and then times unit step function u t minus 2. So transform of 1 over s squared is t, and then at the end we have to replace the t by t minus 2, and then the unit step function u t minus 2. So looks simple enough. So the reason when we recognize that the inverse Laplace transform when we have the exponential, that's where we know that it's required the unit step function. So when we see it in the inverse Laplace transform, and we go from e to negative 2 pi s here, meaning a is equal to 2, we need to do two things. First, of course, we do the Laplace transform of whatever left. I mean inverse Laplace transform of whatever left. But once we have the result, have to replace t by t minus that number. That's the first thing to do. Second we need to do is multiply by u of t minus that number. So just like that. Next, just need to do the inverse transform of s minus 4. Well, that's easy. Where the exponential? Oh, here. Right. By the way, you will recognize that when we have s minus 4, that is another e to the 4t and then 1 over s. Okay, let's just write that formula first. So Laplace transform here of 1 over s minus a, I mean the formula is over there, is e to the at. Notice not this a, this, I'm talking about this 8, which is 4 here. So so the Laplace transform of 1 over s minus 4 is e to the 4t. And then we have to replace the t by t minus 2, and then the unit step function of t minus 2. Right, so we're going to put t minus 2 in here. We have a to the 4 t minus 2 and then u of t minus 2. Right, simple enough. Right, so find the inverse Laplace transform when we have e to the negative pi s. Well, a is equal to pi. So first thing we do, two things, but we're going to have Laplace transform of what's left of the problem. Then we do two things. First, whatever the transform is, replace t by t minus that number, and then u of t minus that number. So the e to negative as, the inverse transform, we have two things. Right, the transform of s over s squared plus 9, so that is the cosine. So we will have 9 is 3 squared, right? So this is cosine of 3t, but we have to replace t by t minus pi and then u of t minus pi. Right, substitute that in for t. Multiply it out, cosine 3t, 3 pi, u of t minus pi. Right, cosine of a difference. Cosine, we have the same function, but different size. Sine, we have the different function, but same sign. So cosine will be cosine of 3t, cosine of 3 pi. If it is subtracted, that will be a plus cosine of 3t. That will be sine 3t, sorry. Cosine plus sine. Both of them are still multiplied by the unit step function u t minus pi. Right, cosine 3 pi or cosine of pi. That is -1, and sine of 3t, that is 0. Yeah. Of course, you can just put in the calculator, make sure that 0, 1 pi, 2 pi, 3 pi. So cosine 3 pi here, cosine the x value is -1, sine the y value is 0. Right. That gives us negative cosine of 3t u t minus pi. Right. Next, we have this one. So if we ignore the e to -3s, by the way, that will be a is 3. Laplace transform of what's left. And then the e to -3s, the transform of that will be equivalent to, whenever we do the transform, replace t by t minus that number, and then u of t minus that number. Right, so what is the transform of this? Of course, if we look in the table, we do have that, which is in this form. Right? Sorry, if it is just a number, I mean in this form. Right. But notice that if we go back to section 7.4, there's another transform. There will be another transform here. If we replace s minus 1 here, that we can transform into e to the t, 1t. In that case, we just have the transform of what's left. Right, so the transform of s minus 1, if we replace s minus 1, if we replace the s to s minus 1, the price to pay is e to the 1t. But notice that when we do all of that, make sure that at the end we have to replace t by t minus 3, and then unit step function u of t minus 3. Still have to have that. Right? Now, so e to the t, which is good. Notice that here we can take out the 5, right? Now, on the top, of course, is 1. S square, 3 we can write as square root of 3 square. Whenever we do all of that transform, replace t by t minus 3, and then u of t minus 3. Right. Notice that, of course, we can use that formula, but if we have a number over s square plus something square, I mean a number, so it will be sine a number, and then the number square. So whatever number on the top, must be equal to the same thing as this. So we need to have square root of 3 top and bottom. So we will have 5 over square root of 3 e to the t, and then Laplace inverse Laplace transform of square root of 3 over s squared plus square root of 3 square. When we do the transform, t is replaced by t minus 3 and then u of t minus 3. Right. Now Laplace transform of that, use the formula will be sine of 5 over square root of 3 e to the t sine square root of 3 times t, but need to replace t with t minus 3. And when put all together, we have 5 over square root of 3 e to the t sine square root of 3t. Replace t by t minus 3, so t minus 3, t minus 3. Let me rewrite this so you can see better. E t minus 3 sine square root of 3 t minus 3, and then u of t minus 3. Right. So that's what we have. Right. Yeah. So notice that when we see the e inside, that will have equivalent to two things here. When we have the transform of s minus something, I'll replace that. When we do that, it's just like multiply by e to the t. So go back to section 7.4 if you want to review that. Right, now I go back to a problem where we have the initial value problem. Solve the initial value problem, that where the input function f of t is equal to 4t from 0 to 1 and 4 when t greater than 1. So still the same thing. Find the Laplace transform and then solve for y of s and then take the inverse Laplace transform. So, but in this case, it is the unit step function. It is the piecewise function. So we have to rewrite the piecewise function using the unit step function and the windows. So first we have the windows from 0 to 1. Well, that is this. And then 4 when t greater than 1. Now we just need the unit step function instead of the window function. So for t, u of t minus u of t minus 1, and then plus 4. Right. Multiply that out, and we let this equal to 0, equal to 1. Multiply that out, 4t, and then we combine like terms. That's what we have. So we put that on the right hand side. Laplace transform of the left hand side, Laplace transform of the right hand side, which is the Laplace transform of this. Right, so Laplace transform of 4t is easy, but Laplace transform of this, for this one, will equivalent to e to the negative s. But then we have to find g of t plus 1, t plus g of t plus a. Right, and then Laplace transform of t plus a, which is negative 4t, and turn out to be this function. Y of 0 is 1, y naught of 0 is 0. So Laplace transform of second derivative, y of 0 is 1. So this is s, and y naught is equal to 0. So notice there is an s here, right? I will add that to the other side. That's where the s here comes from. Y of 0 is 1. So s times 1 is s, add that on both sides, we have s. So that's what we have. And finally divide by s squared plus 4 on both sides. So that's what we have. Once we have the function, we will find the inverse transform of this to get the answer. By the way, before we do that, we'll find the partial fraction of 4 over s squared plus s squared times s squared plus 4, because those two are the same. If I can find the partial fraction for that, I can have the partial fraction for that as well. Right, partial fraction is easy. Multiply by the common denominator. After you solve for that, the breakdown is a and c equal to 0, b is 1, e is negative 1. Meaning the partial fraction a is equal to 0, b is equal to 1, c is equal to 0, e is equal to negative 1. So that is decomposed into that partial fraction. So in this case we have two parts. The first is 4 over s squared times s squared plus 4 decomposed into 2. Same thing here. Just happen to have 4, so that also here, right? And now find the inverse Laplace transform. Inverse Laplace transform of that, this is an odd function, so it will be cosine of 2t. Inverse Laplace transform of 1 over s squared, that's a t. Inverse Laplace transform of this, negative 1/2 sine of 2t, and e to the negative s. Just transform of what left, but replace t to t minus 1, and times the u of t minus 1, a is 1. So Laplace transform of 1 over s squared is t. Laplace transform of this is 1/2 sine of 2t. Right, then put t in here for t minus 1 here for t, and then we have that. That is the function. Of course, we can write this back into the unit step function if we want to. Right. So this will be cosine of 2t plus t minus 1/2 sine of 2t. And then we have this. It will be equal to 0 if it is less than 1. And it will go to the whole function here. When t greater than 1. Yeah. If we can write that into a piecewise function. So that is the answer. Right. And so in the idea is not that bad. Find Laplace transform, solve for y of s, and then inverse Laplace transform. What makes this a little more complicated is that here we have to rewrite the unit step function, and then we have to find the Laplace transform for that. And after that, we find the Laplace transform. When we do the inverse Laplace transform, that involving the unit step function also. Right. Let's look at this problem. So we have the initial variable problem. The input function, however, is a piecewise function. So that's exactly what we've been doing in this section. So first, we'll convert this piecewise function into a function using unit step function. Right. So this will be easy. Just rewrite the function. Right, the function we use the windows 0 from 0 to pi and 3 cosine t for the windows outside. This is greater than, so we're just going to use a unit step function t minus pi, or that go to 0, so we just have this. Right. Now, the step to solve this problem, just like any problem using Laplace transform. First, we find the Laplace transform. So I will write the equation again. F of t is going to be 3 cosine of t u of t minus pi. Right. Now we apply the Laplace transform. Cosine t u of t minus pi. Right. So just like what we have been doing, when we have u, the unit step function, we'll convert that into e to the as, negative as. Here a is equal to pi. And then after that we have to transform 3 cosine t. This is g of t, but we need to do the transform of g of t plus a. So let g of t be equal to 3 cosine of t. So now g of t plus a, or g of t plus pi, equal to 3 cosine of t plus pi. Now we use the sum of cosine of a sum, that gives us 3 cosine t cosine pi minus sine of t sine of pi. Cosine pi is equal to -1, and sine of pi is equal to 0. So that just gives us -3 cosine t. Right. Now to transform. Transform of this is transform of the derivative plus the transform of the function. And now if we write like this, we just need to write the transform of the -3 cosine t. E to negative pi s. Right? So instead of we take the u transform of the transform of unit step function is e to negative pi negative as, and then transform of the g of t plus a instead of g of t, and that is what we have here. Right, transform of derivative. This is going to be s times y of s minus the initial values. If we look at the transform of the derivative, that's what we use. Transform of the function. And now transform of this, I'll take out the -3 and transform of cosine t. Cosine is even, so transform is going to be s squared plus 1 squared e negative pi s. Right, so transform of cosine. Right. Now, the next step is, of course, we solve for y of sub s. Y of 0 is equal to 5. And so we factor out y sub s. Factor out y sub s, we have s plus 1 minus 5 equal to, let's say, negative 3s e to negative pi s squared plus 1. Right, move the 5 over and then divide by s plus 1, and we should have y sub s. And then divide both sides by s plus 1, we have y sub s equal to 5 over s plus 1 minus 3s s squared plus 1 e to negative pi s. Of course, we cannot combine this with that. We divide by s plus 1 this way. This, of course, reduced fraction. We're not going to do any partial fraction with this. We only need to do a partial fraction for the 3s. Okay. Right, so we have 3s s squared plus 1 s plus 1 equal to, there's only two factor, two reduced factor, s plus 1 s squared plus 1, and if a bs plus c. Right, since we don't have a lot of space left, let's just divide the page in two. Right, multiply both sides by the common denominator of s squared plus 1 times s plus 1. We will have 3s equal to as plus 1 as squared plus 1 plus s plus 1 bs plus c. Right. Now multiply it out. As squared plus a plus bs squared plus cs plus bs plus c. Right, combine like terms. 3s a plus b s squared, and here we have cs plus bs then plus a plus c. Right, and then we just match the coefficient. There's no s square on this side, so a plus b must be 0. B plus c equal to 3. And then a plus c will be equal to 0 as well. Now this will be easy. Add side by side here, b plus 2a plus b plus c. But anyway, just put in the calculator. That's simple enough. So put in the calculator second matrix, reduce row echelon form, apply to the matrix and have 3 rows, 4 columns. Right, that 1, 1, 1, 1, 3, 1 here, and 1 there. Right. Alright, convert to fraction. So when we do that, because we have a equal to negative 3/2, b is 3/2, and c 3/2. So we can write y sub s equal to 5 over s plus 1 and then minus, let's just write e to the negative pi s, right, minus e to negative pi s, and then the 3s over s squared plus 1 and s plus 1, use the partial fraction, we have negative 3/2. S plus 1 plus, I would split this and I would write 3/2 s squared plus 1 plus 3/2 s squared plus 1. By the way, this should be the answer, but the next step, of course, we will do the inverse Laplace transform. Right. So transform this back, we should have y of t equal to, of course, inverse transform of that give us y of t. Now just transform of everything, take out a constant. Inverse transform of 1 over s plus 1 and now this. When we see this in the transform, let me just write this. If we have the transform of e to negative pi s and then something, what we see is we can rewrite this as the u t minus pi, and we just do the transform, inverse transform of what's left, but then we have to replace t by t minus pi. So in this case we will have minus transform of inverse transform of this, I will write as negative 3/2 1 over s plus 1 plus 3 half s 3 half s over s plus 1 s square plus 1 sorry plus 3 half 1 over s square plus 1. We do that, but because of the e to negative pi s here, we have to replace t by t minus pi, and not only that, we have to multiply by u of t minus pi. Transform of 1 over s plus 1, that is a e to negative t, and now we have negative u of t minus pi. Right, now we just transform the rest. Negative 3 half transform of 1 over s plus 1 is e to negative t plus 3 half s over s squared plus 1, that is an odd function. Transform being even function should be cosine of t, and then plus 3 half sine of t. But of course, when we do this, t have to replace 2 by t minus pi. Yeah. This is the answer, by the way, so we should get that. Right, actually, that is the same. Right, now, this we can write as 5 e to negative t, and then subtract. Since we have u of t minus pi here, we can write that as a piecewise function. We have 0 on the top when t less than pi. Yeah, that's what the unit step function. And then the other one we will write negative 3 over 2 e to negative t. Instead of t, we use t minus pi. And then plus 3 half cosine of t minus pi plus 3 half sine of t minus pi. And when we combine these two together, we have that answer. Right. So, yeah, the e to negative pi s turn into the u to t minus pi. That's the first part. The second part is we just do the transform of what's left. What's left? When we do that, the t will be replaced by t minus pi. So if we do that, and the transform of this will be negative 3 half, that e to negative t, that cosine t, that sine t, and then we put t minus pi into t, and the unit step function turn into a piecewise function. 0 when t less than pi, and will be that where t greater than pi. And when we add that to the top and bottom, this is what we have. Yeah. Right. So with that, I stop section 7.6 here. As always, thank you for watching, and see you in another video in differential equations.